Welcome again. I'm your lecturer, online lecturer Frank Jacobs, and we are continuing with statistics. We are chapter 9. We're looking at sampling distributions. Sampling distributions. What's a sampling distribution? A sampling distribution is created by, as the name suggests, sampling. The method we will employ under rules of probability and the laws of expected value and variance to derive the sampling distribution. For example, consider the roll of two dice, 1 and 2 dice. A fair die is thrown infinitely many times, but the random variable x is equal to number of spots on any throw, the number of spots on any throw. The probability distribution of x is, for one die, x 1, 2, 3, 4, 5, 6, and the probability in each case is 1, 6, 1, 6, 1, 6, 1, 6. So we can find the mean of xp of x. Xp of x, as shown here, will give you 3.5. The variance, sigma squared, is equal to x minus mu squared times p of x, which calculated in the usual manner, gives you 2.92. And the standard deviation, the square root of the variance, is 1.71. Right? Now, sampling distribution of two dice. A sampling distribution is created by looking at all samples of size 2, n equals 2, that is 2 dice, and their means. And you see the distribution table here. The sample 1, 1 on one die, on one on the other die, 1 die, 2 on the other die, and so forth. You can say the first number represents a number on the, call it die 1. And what you do, you're going to add the total of phase totals and divide by 2 to find the mean. That is shown here, x bar. So in other words, this table gives you a distribution of x bars. Distribution of x bars. While there are 36 possible samples of size 2, there are only 11 values for x bar. 11 values for x bar, and some example x bar equal to 3.5 occur more frequently than others. That is, x bar is equal to 1. That is just an observation. Now, the sampling distribution of two dice. So look at the sampling distribution, the x bars, the various values x bar has from the table is 1.0, 1.0, where's my cursor? 1.5, 2, 2.5, 3, 3.5. We look at the various the probability. The probability is 1 over 36. The probability that the mean is 1.0. That only occurs once, 1 over 36. So these are the corresponding p of x bar. So you have x bar and p of x bar. So if you find the mu of x bar, the mean of the x bars, or the expected value of the x bars, this would be given by the, with my cursor, the sum of x bar times p of x bar. That is, each x bar, as shown here, multiplied by its corresponding probability, and you sum the result. That gives you 3.5. That whether you throw 1 die, 2 die, n dice, the mean value is going to be 3.5. So the mu of x is going to be just mu. Sigma squared of x bar, that is the variance of x bar. You're going to calculate the variance. X bar is a variable there, not x. So x bar minus mu of x bar squared times the probability of x bar. This is using the long form of the formula, and that gives you 1.46. And the standard deviation of x bar, sigma sub x bar, is shown here. The square root of the variance of x bars is equal to the square root of 1.46 gives you 1.21. Comparing the distributions, this distribution is uniform, and this distribution is normal distribution. Distribution of x bar is normal. So the result is that the mu of x bar is equal to the population mean, and that is the mean you get when you do 2 dice is the same as the mean for 1 die. The expected value for 1 die, E of x equals mu equals 3.5 for 1 die. E of x bar is equal to 3.5 for n equals 2. The results are that mu of x bar equals mu, as well as that sigma squared, that is the variance of x bar, is equal to the population variance divided by 2. In this case, it was 2.92 and divided by 2. We got the variance of x bar was 1.46. And you'll see generally what's happening. We can generalize the mean and variance of the sampling of 2 dice. Mu of x bar is equal to mu, as we see. We've seen before, the variance of x bar is sigma squared over 2. For n dice, mu of x bar is going to be mu, as we said before. And the variance of x bar is going to be the population variance divided by n, the number of dice. So if you toss 5 dice, the variance you could calculate would be the population variance 2.92 for 1 die divided by 5. The standard deviation of the sampling distribution is called the standard error. That is, the standard deviation of the sampling distribution of the population of the sample mean is called the standard error. Sigma of x bar is called the standard error and is given by sigma over the square root of n. This you're going to be using quite a bit in working out the associated problems. Central limit theorem. The sampling distribution of the mean of a random sample drawn from any population is approximately normal for sufficiently large sample size. The larger the sample size, the more closely the sampling distribution of x will resemble a normal distribution. Again, on the central limit theorem, if the population is normal, then x bar is normally distributed for all values of n. If the population is non-normal, then x bar is approximately normal only for large values of n. In many practical situations, a sample size of 30 may be sufficiently large to allow us to use the normal distribution as an approximation for the sampling distribution of x bar. Summarily, mu of x bar equals mu sigma squared of x bar is sigma squared of n. The variance of x bar is equal to variance, population variance divided by n. And the standard error, standard deviation of x bar is equal to sigma over the square root of n. 3. If x is normal, x bar is normal. If x is non-normal, x is approximately normal for sufficiently large sample sizes. Note, the definition of sufficiently large depends on the extent of non-normality of x, heavily skewed or multimodal. Finite populations. Finite populations, there is this is addressed. It's not, we haven't been using this in this course. This is just in passing. This is we've shown that the mean of standard distribution is always equal to the mean of the population, and that the standard error is equal to sigma root n for infinitely large populations. However, if the population is finite, the standard error is given by this: sigma x bar sigma over n times big N minus n over big N minus 1, where n is the population size, and the square root of n minus n over n minus 1 is called the finite population correction factor. If the population size is large relative to the sample size, the finite population correction factor is close to 1 and can be ignored. As a rule of thumb, we will treat any population that is at least 20 times larger than the sample size as large. In practice, most applications involve populations that qualify as large. As a consequence, the finite population correction factor is usually omitted. There are several applications that deal with small populations. Look at section 12.5, and we look at some of these. An example. The foreman of a bottling plant has observed that the amount of soda in each 32-ounce bottle is actually a normally distributed random variable with a mean of 32.2 ounces and a standard deviation of 0.3 ounces. If a customer buys one bottle, what is the probability that the bottle will contain more than the labeled count, more than 32 ounces? You want to find the probability x is greater than 32. Where x is normally distributed with mu equals 32.2 and sigma equals 0.3. The probability that x is greater than 32, we convert to z, standardize. The probability that x minus mu over sigma is greater than 32. This is x minus 32.2, which is the mean, divided by 0.3, which is the standard deviation. That is, the probability z is greater than minus 0.67. Read from the tables in the usual way, that gives you 0.7468. That is, there is a 75% chance that a single bottle of soda contains more than 32 ounces. The foreman of a bottling plant has observed that the amount of soda in each 32-ounce bottle is actually a normally distributed random variable with a mean of 32.2 ounces and a standard deviation of 0.3 ounces. If a customer buys a carton of 4 bottles, that is n equals 4, what is the probability that the mean amount of the 4 bottles will be greater than 32 ounces? You want to find the probability that x bar, mean, is greater than 32 ounces, where x bar is normally distributed random variable mu is equal to 32.2 and sigma is equal to 0.3. Things we know. X bar, this is supposed to be x bar, is normally distributed. No, x is not, the population is normally distributed. And x is normally distributed, therefore, so will x bar. X bar will be normally distributed. We too know that mu of x bar is equal to mu is equal to 32.2 ounces. 3, that sigma of x bar is going to be sigma divided by the square root of n. Sigma is 0.3 and n is 4 and the square root of 4 is 2. 0.3 divided by the square root of 4 is 0.15. So we have all the data we need. So the probability that x bar is greater than 32 is given by probability x bar minus mu of x bar over sigma of x, that is z. Probability z is greater than 32.2 minus 32.2 over 0.15 gives you probability z is greater than minus 1.33, which gives 0.9082. Remember, you read the tables accordingly in the manner we've done before to give you 0.9082. That is, there is a 91% chance the mean of the 4 bottles will exceed 32 ounces. The dean of the School of Business claims that the average salary of the school's graduate 1 year after graduation is $800 per week with standard deviation of 100. A second-year student like to check whether the claim is correct. He does a survey of 25 people who graduated 1 year ago and determines their weekly salary. He discovers a mean of $750. To interpret his findings, he needs to calculate